If you've ever taken a science class or a physics class or a chemistry class, you might have heard of this term, and we call it electromagnetism. I know it's a pretty long word, but it's a very interesting term, and the field of electromagnetism is honestly fascinating. But what actually is electromagnetism? Well, to put it short, electromagnetism is just the energy that is emitted by waves. More specifically, electromagnetism is kind of the field that we deal with when we're talking about visible light and infrared waves, and basically we like to study how energy is transmitted through waves, and it kind of gives us this whole other perspective where we can deal with things not so much in the particle domain, so like rolling a ball across the floor, but in the wave domain. And yeah, when you look at a ball in the particle domain, you would say it has energy, kinetic energy, if it's rolling across the floor. But with waves, energy can behave differently. So particles and waves are two different domains, but we still deal with energy in both, just in different ways. We take different approaches to deal with it. And in this video, this is actually part of a two-part series. I'm going to be releasing another video later today. But it's basically going to be dealing with electromagnetism, and we're going to kind of dive deeper into the chemistry aspect of things. And we're going to talk about, quantum numbers and basically the arrangement of electrons around an atom. And I had to kind of split this into two videos because they are longer. And I thought it'd be a good idea to just, give you guys two different videos to watch, and you can just watch whichever is specific to your questions. But yeah, electromagnetism, very fascinating. I'm actually going to pull up a chart in a second so you guys can become a little bit more familiar with what we're dealing with here. So as you guys can see here, this is a typical electromagnetic radiation chart. So we start with radio waves, and they're typically the longest. Well, they are the longest, as we can measure here. You can see that they're pretty long, but as you go from left to right, you might notice that the waves become shorter in length, and that's because when you go from left to right, you increase in energy. And we're going to talk about, wavelength and parts of a wave and what determines if it has a lot of energy or if it doesn't have a lot of energy in a moment. But I kind of just wanted you guys to get a better idea of what we're dealing with here. As we increase in energy, so as the waves get shorter, we typically see more dangerous waves because the high energy can be so unstable that it's typically more dangerous to deal with as opposed to something of short wavelength, or of long wavelength, like radio waves and microwaves. So now that you're all a little bit more familiar with waves and electromagnetism and what we mean when we talk about electromagnetic radiation, we can actually describe the components of a wave itself. So when we're dealing with what we're going to be talking about today, which is relating energy and electrons and energy quantization, that is going to be dealing more with the wavelength and the frequency of a wave, but we can still draw some of the components of the wave so you can be a little bit more familiar with it. So actually, if we draw a line down the middle of the wave, I know this isn't the best illustration of a wave, but just try to pretend it is. It's hand drawn, so not going to be perfect. Anyways, when we're looking at a wave and we look at the peak, which is this point, the highest point the wave reaches, and we measure the distance between the peak and this middle line here that we drew, we look at that. That's called our crest. So the crest is the distance between the middle to the peak of the wave. Conversely, when we look at the length or the distance from this line to the bottom of the wave, that's going to be our trough. So that's our trough right there. So crests and troughs, they are almost like opposites, kind of. So crest is the distance from the middle to the top, trough is from the middle to the bottom. But what we care about is actually the wavelength is the first thing that we care about. So the wavelength is the distance between one point of a wave, and then you let it do one cycle to the next point. So if I wanted to say the distance between this peak and this peak, well, that distance there is going to be a certain wavelength, and it will usually be in nanometers. Let's do this point right here. You would let it do one cycle, and it would end up here. That's going to be another wavelength right there. And it will typically always be the same. Actually, it will always be the same distance, unless the wave is, the wave is changing in oscillation, then it would be different. But for a standard wave, in this case, it's going to be the same distance for that specific wave. And the higher the wavelength, so the higher the wavelength, the less energy that wave is going to have. So higher wavelength, the lower the energy. Then we also look at the frequency. So the frequency of a wave is how often does the wave oscillate. In other words, how often does the wave complete an oscillation or a cycle. Let's draw this wave here, and then let's draw this wave here. And when we're dealing with frequency, we always look at a certain unit of time, a measurement of time. So like a second, for example. Let's say we let this wave run for 1 second, and you can see it only oscillates once, right? It only goes from here, then it oscillates, then it ends here, but it only goes around once. But if you look at this wave, it's going to go around, let's see, 1, 2, 3, and a little bit more. So this is like 3.5 oscillations, and this is just one oscillation. Well, obviously this one's going to have a higher frequency because more waves are elapsing in 1 second. And the unit we measure, or the unit we use to measure oscillation, that's called the hertz. So just to recap over here, when we're talking about wavelength, we use this symbol, this Greek symbol called lambda, and that's used to talk about the wavelength of a wave. And again, we typically use nanometers to describe it. And then hertz, let me just write wavelength. And then hertz is used to describe the frequency of a wave. And that tells us how often it's oscillating. And we can actually use these two variables here to kind of help us understand the energy that an atom has, and the energy of a photon, and sorry, not the energy that an atom has, but rather an electron has, the energy of a photon. And yeah, we can do some really cool things with these variables that kind of helps us understand a little bit more about electromagnetism. So one of the first equations that we can use is actually C equals lambda times V. And what this equation basically tells us is we can relate the wavelength, the frequency, and the speed of light with each other in this equation. And when we use this equation, it's important to note that this is specific to how waves behave in a vacuum. So we're not dealing with did I spell that right? Yeah, there we go. Vacuum. So this is specific to a vacuum. So we're not having any particles colliding with the wave. We don't have any kind of clutter or nothing like that. Just a pure vacuum. We can relate the three variables with each other. So that's the first equation that we deal with So another one that was developed is we can actually relate the energy of a wave. So E is equal to H times V. V, again, is the frequency, but H is actually something we call Planck's constant. And this equation here was actually developed by Max Planck, and he was basically able to determine the energy of a wave just with its frequency, and he eventually developed Planck's constant, which kind of just tied everything together, which eventually helped, hundreds of scientists later on study electromagnetism. So it really was a huge innovation within the electromagnetic field. But yeah, these are some of the equations that we use to kind of relate light and its components. And we're eventually going to bring all this into something called the Bohr model, which is more specific to chemistry. So the Bohr model is a model developed by Niels Bohr. He was a chemist who kind of took the studies of Max Planck, who we just talked about, and Albert Einstein, and he developed this thing called the Bohr model. And the Bohr model is basically how he modeled the hydrogen atom. Like at the time when he was doing this, people didn't really have an accurate understanding of the atom. But this is specific to hydrogen, and it's so famous because of how much of an innovation it was, rather, at the time. And this is something that we might have heard as a planetary model. And the reason we call it the planetary model is because, well, we have the nucleus in the center, and then we have the electron, a negatively charged electron, orbiting the nucleus. But Bohr ran into a problem. You see, according to classical electromagnetism, if something is accelerating, then it must be emitting radiation. But since the electron is technically orbiting and it's accelerating, then technically it should be constantly emitting radiation, meaning that it's constantly emitting energy, but that's not possible because energy is not created nor destroyed. So he was puzzled with this paradox here, so he just flat out ignored the classic electromagnetics, and he said, well, how about instead of energy, what if these electrons actually emitted photons? Photons, which is a discrete form of energy that is emitted when the electron jumps orbitals. And orbitals, you may have seen, are just these, in simple terms, these rings around the atom. So actually, let me draw a better picture here. These rings. So when one of these electrons jumps to the next one, it's going to have a change in energy. It's actually going to have a shift in energy, and it's actually going to increase in energy. So the electron is not emitting energy when it's orbiting the nucleus, but instead it's gaining or losing energy when it increases or decreases in excitement, and therefore it changes its shell or its orbital. We call these N shells. And what's interesting about these shells is that they come in quantized amounts. And quantization, it actually comes from the word quantization, means that electrons can only be in one discrete form or unit of, or one state rather, of energy. So they can't exist between shells. No, they have to be on either the first shell, the second shell, the third shell, etc. They can't just exist between them. So eventually a man by the name Johannes Rydberg came to develop this formula where he basically related he related, one second, he was able to relate the wavelength of the energy, or the photon rather, emitted by an excited electron, where he basically said, well, hey, if you take the lower energy shell minus the higher energy shell, and you take their inverses squared, or you square them, and then you basically take their inverses, so 1 over each of them, and then you multiply all of this times the Rydberg constant, that's going to give you 1 over the wavelength. So he was basically able to relate all of this, and this is, again, specific to the hydrogen atom, because once we look at atoms with more shells and more electrons, it gets a little bit more complicated, but this is specific to the hydrogen atom, and it allows us to make certain predictions about the wavelength of certain photons and waves that are emitted when an electron becomes excited. So it's pretty interesting. We're going to go over a quick summary here, so let me just erase all of this. Okay, so just a quick little recap. When we have a wave here, we're going to have the crest and the trough, and we're also going to have wavelength, which is represented like this by lambda. Then we're going to have V for the frequency, which tells us how often does the wave oscillate. And then we use hertz to describe that. Then we're also going to have our first equation, which is C equals H times V, or, sorry, not H, lambda times V, and that basically tells us the speed of light equals the wave's wavelength times its frequency. Then we also have energy equals Planck's constant times V, or energy equals, that V, that C is equal to wavelength, or lambda times V, and we can derive V as speed of light over wavelength, and E must be equal to, in other words, H times C over lambda. And again, C is just the speed of light. So yeah, this is our first formula here. Our second one's here. And then finally, this kind of more complicated one, which is, sorry, actually, I'll write it over here. 1 over the wavelength equals Rydberg's constant times 1 over n1 squared minus 1 over n2 squared. N1 equals the lower shell, and N2 equals the higher shell. And it's important to know what all this means. And if you're still confused, or you're not really sure what's going on with these shell things, don't worry. Next video we'll have all of this, and hopefully it'll make it easier, but I'm gonna go a little bit more deep with this kind of subject matter so that you can understand it better. But yeah, the next video will all be about quantum numbers, shells, and all that kind of stuff, to kind of help you, give you a better idea of what's going on in this video, so you can go back and forth watching them to kind of familiarize yourself a little bit with what we're talking about. And again, we also had the electro, it's a little big, go electro, magnetic spectrum. And that's the spectrum I showed you guys with the different types of waves and the visible light. And finally, we have the Bohr model, which is just is specific to hydrogen. Remember that hydrogen nucleus with the outside electron, and it basically, whenever a photon gets excited or it gains energy, it's going to jump orbitals, or sorry, not orbitals, but rather shells, and we call these N shells. And remember, N shells are quantization examples. So I just want to comment real quick that electromagnetism is by no means an easy subject. It really requires extensive review, and this shouldn't be the only video that you watch. You should really use as many resources as you can to kind of familiarize yourself more with this. It really is a tricky, tough concept. I will be releasing again part 2 shortly, and it will cover topics such as quantum numbers, shells, and the structure and how we kind of position electrons within an atom. But with that, that's going to be the end of this video, and I hope everyone has a good rest of the break and a Happy New Year. We're almost in 2026, so it'll be fun. But yeah, thanks for watching.